Well, friends of mathematics, we're talking about section 3.1, quadratic functions. And to be a quadratic function, the highest power of x, or our independent variable, maybe t, is 2. And all non-negative integer powers otherwise. So we can have zeros, we can have ones, we can have twos, no square roots, no thirds, no things of that nature. So when we talk about a quadratic, we're usually looking at something that's in standard form. And we'll say, just to use like variables that we're comfortable with, ax squared plus bx plus c. We refer to a as our leading coefficient. And what's nice about a is if a is greater than 0, then our graph is concave up, that we're going to have some quadratic that opens upwards. Similarly, if a is less than 0, the graph is concave down. So that's what our a value does for us. There's another very nice value when we're in standard form, and that's c. And c is our initial value. So that when x equals 0, f of x, and I guess we could say y is equal to f of x, is c. All of these terms drop out and we're left with our final term. If I was going to make a very quick picture here, just for us to think about things, say we went through the point 0, 5, and it looked something like this. You know, I don't know a lot about this, but we could have y is equal to some ax squared plus bx plus, and we certainly know that c is 5. The other thing that we know here is that in this case, a is less than 0 because our graph is concave down. So if I start out with some quadratic function, let's say f of x is equal to, 3x squared minus 14x minus 5, what I can do is I can begin to put this into factored form from here. Now, I'm not going to talk about how to factor today, but I can say that we're going to have our two factors, 3x and x, because that's going to be multiplied to give us x squared. There's certainly going to be a 5 and a 1, and we can see that the 3 and the 5 have to do the dance to get that 14. And we're done. If I wanted to go one step further here, what I might do is I might factor out the 3 out of this pair so that I get 3 times x plus 1/3. You can see I pulled that 3 out of each times x minus 5. And while this is not a move that I typically want to do, when I think about factored form, I write it like this. Factored form will be f of x is equal to a, x minus r1, where I'll call r1 a root, and x minus r2. Okay? And note that this a value is the exact same a value that we have in standard form, ax squared plus bx plus c. That if a is a positive number, our thing is concave up. If it's a negative number, it's concave down. Now, when we have roots here, our function is going to pass through, when x plus 3, look, if x is equal to negative 1/3, this whole term will be 0. And so we're going to have a 0 at x equals negative 1/3. Similarly, when x is 5, this whole term will be equal to 0. And we know that our function is concave up, and so a very quick sketch of this function right here gives us, Here's our graph. Now, I don't care which form we're in, but I will say that factored form is much more useful in making a picture, in playing with these things. We can refer to these as zeros. We can call them roots. We can even call them solutions. And it's nice to have this because I can set it equal to 0, and then each of these terms equals 0, and we can also figure out where things are. Now, the last puzzle that we want to talk about here is, suppose I gave us a graph and I told you where some of the roots were. Suppose I have a root here at, say, -3, 0, and let's have one here at, I don't know, 5, 0. And let's go something like this. And suppose I gave you some other point, and maybe that point will be, I don't know, 3, 2. So what can we do given this picture to make the formula? Well, we can certainly say that we're going to have some a value. And the reason it's going to be some a is that really there's an infinite number of quadratics that have roots at -3 and at 5. And so I'm going to make that entire family right now x plus 3. Note, when I put a -3 in for x, it's going to 0 out. And so, or we could also say that I made a left shift, right, of that root. And then finally, x minus 5. So now that I have this family of quadratics that goes through -3, 0 and 5, 0, I'm going to use that 0.32 in the only way I know how. Well, 2 is an output value. And then 3 is my input. So we'll have 6, a -2. And wrapping this thing in a tux, solving for a, we're going to have -1/6 equals a. Our final answer for this quadratic function that I have pictured for us, not the dashed ones, this original one, is y equals -1/6, x plus 3, x minus 5. And the last thing that I will say here is there is no reason to multiply this thing out. That's something that I would consider to be a waste of life. If I needed to know what the initial value was here and to get the c value, what I could do is I could plug in x equals 0. And let's just do that for fun. Aren't we having fun? -1/6 times 3 times -5. And there are some of you that are puking in your own mouths because I haven't figured out what this collapses as. But let me tell you, friends, this is a fantastic point. 0, -1/6 times 3 times -5. That is an exact answer and more than acceptable to leave on any of your exams here.